Hello and welcome to another video presentation in the CERG Showcase series. I am delighted to welcome Niki Kasier for this presentation. And Niki is a chemistry school teacher and network research lead at the Norwich Research School in the UK. Niki previously worked in science research, traversing the equator multiple times while working as a marine biogeochemist. Niki is particularly interested in threshold concepts which can lead to new or transformed understanding. Niki's also an elected member of the Royal Society of Chemistry's Education Division Council, and this year in 2018 she is a recipient of a CERG Teacher Research Bursary Award. Niki's presentation is on threshold concepts in chemistry and using light bulb moments for learning success.
Hello, my name's Niki Kasier and I'm a chemistry teacher from Notre Dame High School in Norwich. I'm also the network research lead there for the Norwich Research School, which means that I help teachers to access and interpret and to apply educational research. My background is in chemistry and in research. My degree was in chemistry. I did a PhD in atmospheric and analytical chemistry, and then I did a postdoc looking at the interaction between the ocean and the atmosphere, actually in an area called marine biogeochemistry. So I was very much combining chemistry with other disciplines. I became a teacher about 13 years ago and I absolutely love it. But I then started to, miss the research side a little bit, and a few years ago, I think probably when I was on my third maternity leave, I started to really kind of become interested in research around education and chemical education. Originally, I think more general methods, probably through people like Simon Lancaster on Twitter and the chemistry vignettes they were doing. I was really interested in whether flipped learning would help with some of my teaching, and it's something that I still use to a certain extent in certain discrete areas within my teaching. And also around the same time I started to read other general kind of research articles and articles about research that I found really interesting, particularly around the idea of desirable difficulties with Bjork and the idea of kind of learning versus performance, but also I was really interested when Professor Rob Coe published a report about how tricky it is to observe learning. Rob Coe's poor proxies for learning, which basically said that just because students are doing a lot of work, just because they are busy, it doesn't actually mean they're learning something, felt really revolutionary actually at the time. It was very different to the messages I was getting elsewhere, and I think that's when I really started to kind of read more about the ideas behind research. And so from that I started a journal club at school, which is still running now actually, which encourages people within my school to look at research. I started to kind of present ideas that I'd found at department meetings and so on, and then a couple of years ago an opportunity arose to apply to be a research school, and we are now part of the Research Schools Network, which is overseen by the Education Endowment Foundation and the Institute for Effective Education at the University of York. And really our remit, or the ethos behind the Research Schools Network, is that schools listen to schools and teachers listen to teachers. So we really work alongside teachers to help them to evaluate and implement research in their teaching. My interest in specific chemistry or chemical education research came kind of parallel with this. I really enjoy reading the Education in Chemistry magazine from the Royal Society of Chemistry, and I used to read articles in there that kind of flagged up bits of research, and sometimes they led me to investigate further, which is where the threshold concepts interest came from. That was originally from an Education in Chemistry article. But then also I've been really lucky this year to have been involved with the Science Guidance Report, which has just been published by the EEF. It's written by Sir John Holman and Emily Yeomans, but I was part of the panel that helped kind of look at the research that's out there and to turn it into applicable kind of classroom-based activities or classroom approaches. And really that's at the heart, I think, of my interest, that it's a really good starting point, but it is not an answer, it's not a silver bullet, and it is the beginning of the story, not the end.
So my use of specific chemistry, chemical education research starts from here. This is a typical diagram we see at GCSE of a lattice of an ionic compound. And I was using this in a lesson with my GCSE students just as they were about to sit their GCSE exams. It was a review lesson. And, you know, they were doing really well. They were a good set, they performed well, they were getting good marks in all their tests, and I really thought things were going well. And I was talking about the properties of ionic compounds and lattices and so on. And one of them said to me, as I was talking to her, she said, "But Miss, I don't understand where the lattice comes from." And I said, "What do you mean?" And she said, "Well, you've only got 2 ions, so where does the lattice come from?" And I thought, and I suddenly realised that she was thinking of this dot and cross diagram that I'd used to introduce ionic bonding and ionic compounds and ions. And so in a typical dot and cross diagram, there are 2 atoms, they swap electrons or they transfer electrons to form the ions. And she understood both of these things separately. She understood that there were lattices, she understood the properties of lattices, and she also understood how ions were formed, but she hadn't somehow put those ideas together. And literally just as I talked to her and said, "Look, you know, it's actually, this represents millions, billions of ions," I guess I should have said that from the start, then this light bulb just came on. You saw it in her head, and it was a lovely moment. Suddenly all these ideas kind of clicked into place. I think people go into teaching for all sorts of reasons, but one thing that is pretty universal once you're a teacher is that everybody finds these light bulb moments really rewarding, when you've seen a student struggling and they suddenly get it and ideas click into head. It's the most inspiring, rewarding thing. So when I first read about threshold concepts, I really like the idea. They're these ideas, and I first read about them in this article in Education in Chemistry, and threshold concepts are these ideas, these portals to new or transformed understanding. So they're the ideas that once you understand them, other ideas click into place. And we know that as science teachers. I mean, I when I'm talking about the properties of ionic compounds, I have to make sure that my students understand what ions are, what an ionic lattice is. They have to understand that ions are still charged when they're in solution, but they're held rigidly when they're in a solid. But none of this would be any good to them if they didn't first understand that when we're talking about solutions of ionic compounds conducting electricity, electricity or electric current isn't the flow of electrons through a metal wire that they probably learnt about in Year 7 physics. What we're talking about here is a flow of charge. So we know as science teachers that these concepts have to come in the right order, and there are some concepts that people have to understand before they can understand others. And they have various characteristics, according to Mayer and Land from 2003, that they're transformative, so they shift your perception of things, change your values or your attitude. Originally they came from higher education and economics, so it's this idea of values as well as everything else. They're probably irreversible, but that's something I've been looking at actually. They're integrative, they're probably bounded, and I think most importantly for us as teachers, they're potentially troublesome, and sometimes the ideas might conflict with the preconceptions that students have, and often these are the ones that are tacit for teachers as experts, and so if we're not careful, sometimes we don't explicitly teach them or even discuss them. And when we talk about troublesome ideas and so on, I'm really interested in the ideas surrounding Johnson's triangle, about why chemistry as a subject is tricky in nature, and I love this idea of thinking about the macro level, which is where we tend to experience things generally. We see, we feel, we hear, but these are generally caused by things in chemistry on a submicroscopic level, so things that we can't see, we can't experience, and at the same time we represent things using symbols, which in the long run is great. It means that we have this universal language that people can use all over the world, but it's these three levels that students have to move between all the time, and that's one of the reasons that chemistry can be so tricky. And in this paper from Vicente Talanque, he was talking about threshold concepts, and he's very specific that these are different to the traditional kind of big ideas that we have in science. So whereas big ideas have explanatory power, we use them to predict and make decisions, and so on, threshold concepts are different because they actually transform the way of thinking and lead to this profound conceptual change. This is, you know, the threshold concept idea is deeper than just understanding something. And one of the things that he talks about is the fact that when we're moving between the submicro and the macro level, some of the things that we see on the macro level that seem to be ordered or driven by something are often driven by random processes on a submicroscopic level, which can be quite a difficult idea to understand. And he gives the analogy of, for example, when gossip spreads. You know, gossip will spread in a certain direction, as it were, but it's through a series of random conversations. Or if you see a traffic jam building up from above, you'll see the traffic jam building backwards, effectively moving backwards, but the cars that are leading to the traffic jam, they're moving forward. So what's going on one scale is not necessarily the same as what you see or you experience on the macroscopic scale. And so students often think they're being enablers or leaders that lead change, and that's why we talk about, or teachers and students talk about, atoms wanting to lose an electron or wanting a full outer shell and so on. It's really easy to imagine that the atoms have feelings or something. I wanted to see which were the really kind of sticky concepts in the structure and bonding unit, because I was writing a scheme of work at the time that I was reading about all this. And to see if any of them were particularly pervasive or tricky or useful, really, so that I could maybe see if any of them would be counted as threshold concepts. My first step was to look at misconceptions literature. Really lucky as a chemist that there's lots of resources available online via the Royal Society of Chemistry, so that was my starting point. And once I had a list of the common misconceptions, then I made sure that I first of all taught them explicitly as I introduced the unit, but then as I was carrying out my normal kind of assessment throughout the year, either in tests or homework activities or class activities, I made sure that I assessed understanding of these particular concepts, as well as seeing whether students had the right or wrong answers. I wanted to see how confident they felt about their answers and the concepts. So I added in a measure of confidence to each of the questions that I asked. Now, this was purely to help my teaching. It was not a research study, so I've said it wasn't valid, robust, probably reliable, it was probably biased, but my aim was simply to use the research to inform my teaching and to evaluate that to help me know how to help the students that I was teaching at the time. And I really think this is an important part of teaching. I think when you first start teaching, you're like a rabbit in headlights, and you're just trying to work out all the subject knowledge, you know, the things that you've forgotten, the things that you're less confident about. And I remember year 13 lessons when I first started teaching being terrifying in case I was asked something that I didn't know. And then as you move on, that becomes less of a worry, and then you are able to think more about why students understand or don't understand things, and how you can best help them, and begin to anticipate some of it as well. I came up with using the mean confidence difference as well as the proportion of correct and incorrect answers. I ended up with a list of concepts that by order of how tricky students found them, and it was pretty evident that some were more tricky than others. And you know, some of these were surprising, the ones that I kind of looked at, especially the final one. But that comes into this idea, I think, of the novice versus the expert. And Glynis Cousin, in her Threshold Concepts paper from 2006, she talks about having to retrace the journey back to innocence. You know, you've got to think about how you understood or misunderstood things before you became an expert in chemistry or in science. And the problem with these is sometimes they're so tacit that they're done without even thinking, that we don't refer to them enough when we're teaching pupils. To be honest, I'd never thought to emphasise the millions of ions until after thinking about this. And so I did change the way I taught it, this topic, the next year. I made sure that right from the start I introduced models, and I started with the idea of ions rather than dot and cross diagrams, so that right from the start I had those kind of properties and the idea of kind of 3D lattices and ions and so on right from the start. And when I did introduce dot and cross diagrams, I kept referring back to these models over and over again, making the links between the two. And also throughout this, I really came up with a few ideas that I'm very much, that I really emphasise now whenever I teach the topic, and that was all through conversations and just monitoring students' understanding as I went. So the other thing I'm really interested in is what we mean by students learning something, how we know that students have understood a concept, for example, and whether it is something that's irreversible. One of the characteristics that Mayer and Land talk about for threshold concepts is that they are probably irreversible. And this bit starts with Ionic Equations, which I was going through with my year 13s a few years ago. And they were a really good class, bright class. They'd done really well in exams. They'd answered questions on these very well. They knew how to remove spectator ions to come up with net equations and so on, but they just weren't quite happy with it. They weren't quite happy with the idea of what those spectator ions were and why they were removed. And I just happened to have been doing precipitation reactions that day with my year 11, so I just showed them a couple of reactions and just drew some really simple diagrams to go alongside it, so showing the ions that were in solution at the start and at the end, and demonstrating that there were some ions that effectively remained unchanged and were still there, solvated at the end as they were at the start. And again, you just saw this kind of realization happen, because although the class had understood both of these things in separate contexts, they hadn't related these things together. So again, linking that macroscopic level to the submicroscopic processes and being able to link those things together, they hadn't quite done that. And once they did, their understanding deepened. And what was particularly interesting about this was it wasn't just spectator ions that relied on this understanding. We had covered solubility, we'd looked at electrolysis, electrochemical cells, and so on, and again this link hadn't been made, and yet they'd got the answers correct. And I think it comes down to the way that we assess things as much as anything. It does really depend on how you ask the question. So certainly the way that you ask questions is important. And I think it's really important to test the same concept in a number of different contexts and a number of different ways to make sure that students haven't just learned the correct answer, they're not mimicking it. And the other thing is, I think we have to really think about what we mean by learning. I mean, performance is really easy to measure. Performance at a particular time, you can measure it there and then. And if I teach something in a particular lesson and then assess it at the end of that lesson, then often performance is high. But have they actually learned something? Are they going to remember it next week or the week after or the next month or the next year? That's when true learning happens, I think. So that's why another area that I'm really interested in and is cognitive science and how that can be applied to my chemistry teaching. And so I helped to found a group called CogSci, and we're a group of teachers that look at cognitive science in science teaching. Now, this isn't about making things easier, but it's about making it easier to do the things that we want students to do, to get rid of the other stuff and make sure they can really can progress and think about the stuff we want them to think about. So the way that I've used this in my teaching of concepts is things like, first of all, using retrieval practice to make sure that the language that students have to use is much more familiar to them. And I use spaced practice to come back to concepts again and again and review them, try and leave some forgetting into time. Sometimes this is with review homework, sometimes it's just questions at the beginning of lessons, and sometimes I'll put questions at the end of tests and so on, but just making sure things are constantly reviewed over time. And I like this as well because one of the areas that they talk about in threshold concept research is this idea that learning is liminal. And so you take steps backwards as well as forwards. And if we're not careful, that can become something that becomes discouraging. And we can be scared of it as teachers. Whereas I think it's important to understand that sometimes these concepts take a while to embed, and that's not a bad thing, and if you can let students know that and feel less threatened about it, then that's no bad thing. And sometimes spacing things out, allowing them to forget things and come back to them, can help with that. Also, taking into account cognitive load, I'm really interested now in making sure my thinking and their thinking is more explicit, and so using things like worked examples and fading worked examples, and making sure that I talk through what I'm saying and make all the tacit knowledge explicit to students as far as possible. Having said that, as I said, none of this is necessarily an answer, and it's I keep in mind the whole time that I am doing this to help my students improve and to make my teaching more effective. But I'm also very aware that I am, as well as being a teacher, I am a mother and I have a life outside of the classroom. So if any of this is adding to my workload, however efficient or amazing it is in terms of the students, I really think about what I'm doing. So I'm also quite pragmatic. So for example, there was some really interesting research from Sapeda et al. From 2008 talking about what the optimum spacing gap is between study and restudy if you're trying to help students to remember things. And I thought this looks really interesting, and I kind of planned out all of my my year's plan to try and take account of that. And it didn't work. I mean, sometimes it would come in when I had a mock exams or a Christmas pantomime or something. So, you know, as teachers, we can only do what is practical, you know, within the bounds of being professionals within a school and within time constraints. And if you're interested in research as a teacher or an educator, Twitter is a brilliant starting point. There's a few ideas here of people you can begin to look at. And as I said before, there's loads of really good resources on the RSC website that kind of tease out conceptual understanding.